talk about fluidic morphing matter. And so the definition of fluidic. So fluid is a substance that has no fixed shape and yield easily to external pressure, such as a gas or a liquid. So this is a Wikipedia way of saying we are talking about, you know, air and water and oil. And the most common fluidic morphing matter is driven by either air or water. So these two have a lot of similarities in terms of the morphological changes you can get from the actuation, but they are also different because air is compressible, right? And the fluid like water is incompressible. So some of the much heavier load lifting devices are actually made of hydraulic actuation. So hydraulic actuation is a fancy way of saying basically liquid-based actuation. So if you've been to the machine shop, some of the heavy metal cutting machines are actually actuated by water. And there are many pneumatic morphing in our daily life, such as in nature, in living organisms. Frog use this, and some birds as well, to generate sound by basically inflating and deflating an air bladder that's grown on their body. They could attract for mates. And they can also be used in nature for basically positioning themselves. This seaweed kelp, they actually have this gas-filled bubbles. They would help the whole plants to kind of float on top of water so the leaf can get in contact with oxygen. And there are also pneumatics in our daily life. So for example, the balloon you will wear, you would play with in the festivals, or even a tire. And this is becoming a growing interest in the robotics and other engineering fields, broadly speaking, especially as the rise of soft robotics. Pneumatic actuation techniques has been fine studied for the past decade-ish. Especially a lot of those soft robots are inspired by soft body animals in the deep ocean. Octopus, for example, is a very stereotypical organism people study when they talk about kind of soft actuations driven by air or water. But also caterpillars, for example, and different kinds of tentacles, even elephant trunk. These are all stereotypical natural organisms people study and replicate. And this is one of the classic soft robotic works developed in the 2011, so by a team over Harvard, by Professor George Whiteside's group. And then it was one of the first kind of breakthrough in the soft robotic fields. Basically, it's a silicone bladder. You cast silicone into this multi-layer structure, and there's an empty chamber, and you can actuate the 4 chambers in a predefined sequence. And as a way of the actuation, those 4-limb robots will crawl, and they have different modes of crawling. Some just have a slightly lower body to travel through narrower spaces, and some, they can lift up their entire body and walk much faster if there's no physical constraints. And it gets popular because A, it gives some interesting locomotion modalities that those hard robots don't have, but B, because those are actually fairly easy and low cost to make. And they're very accessible. Soon after the roboticists and chemists started to use it, architects and designers also started to leverage it to make even more creative things out of it beyond robots. So I remember some architecture friends started to make those breathing facades. Designers started to put it on body and try to make wearables. I actually have a friend who made a spacesuit. And they actually did a metabolic hyperbolic testing in a fancy flighting experiment. So in that context, pneumatic morphing is also catching up in the field of human-computer interaction. So a lot of them to do with either dynamic haptics or shape-changing representing dynamic information. So on the left, you see this is basically is a screen. By inflating and deflating each buttons, you could get a completely slippery and flat screen. You could also get kind of those buttons pop up to give you specific haptic sensation. And on the right is actually a USB storage device. And so the creator's idea is to use the volume and geometry to represent the amount of data you are storing and transferring from your laptop. So talking about, I want to just briefly mention about the design framework we sort of pointed to before, and then we can see how the fluidic morphing method can leverage this design framework. And this framework is more general beyond fluidic morphing method. So when we think about morphing method, we think about basically the computational design, the engineering design workflow coming from a specific physical input stimuli, and then going into a specific material type. Then you think about the material is being manipulated into a specific geometry or structure, either microscopically or macroscopically, and sometimes hierarchically. And then eventually you get some sort of physical output. So pretty much all the morphing method or dynamic shape-changing materials would follow this engineering design framework. And I will have more examples to show you guys. And then now, this is made up, by the way. So it was pretty, I think, well acknowledged for this framework, this engineering design framework. So this is well acknowledged within many fields, including, material science, robotics, HCII, design. So whoever worked with morphing method, they would more or less agree with me on this framework. So basically, you have an input stimuli. Again, you talk about materials, you talk about structures, you get some sort of a physical output. However, in HCII field, people haven't really rigorously developed a design framework for leveraging morphing method. So that's why I said this is kind of made up. It's a framework our lab and me myself has been trying to develop. So the idea is, when we talk about this kind of engineering cycle from stimuli to output, there's no human in the loop. And we don't know what activities that could generate this input or what's the benefits of having this output. So in this newer framework, we are putting human in the loop. So again, there must be some sort of a situation. Human is in it that triggered a specific physical stimuli. And also the physical output could affect the situation, benefit, augment, alter, etc. of people's perceptions. And you guys all have been a creator of this computational loop. So remember when Leah gave you guys the assignment, she asked you to think about for whom, in which situation, it's a what that did what when being triggered in which scenario. So those are all great examples what you guys did of a human-centered design framework of morphing method. So now let's give you guys some examples of adapting this engineering design framework to fluidic morphing method. Again, we are talking about a purely engineering design framework for now. So if you look at this video, so this is a pneumatic, again, it's a silicone bladder on top of a piece of cardboard paper, and they were bonded together. And if you blow up, really, there is a silicone layer at both the top and bottom, and in the middle, there's a piece of paper with specific folding pattern. So now if you inflate air, it can coils up. And depends on the folding pattern of the paper you are embedding into the bladder, you can get different kinds of bending behaviors here. Some are more like a flat coil, right? Some are more 3D coils. And then depends on where you locate those air bladder, you could also transform a flat shape, either linear or circular, into interesting 3D shapes. So in this case, as I mentioned, it's very simple. So there's an air bladder on top, crisp paper in the middle, folded paper, if you will, and also a silicone coating at the bottom. And if I try to fit this into the engineering design framework, right, the physical input is air stimuli, the material is silicone and paper. And there's also a geometry aspect, that's the folding pattern. And then the physical output is this pre-programmed bending curvature. So I wanted to mention that depending on your field, you might feel comfortable to manipulate one or multiple of those components within the design framework. For example, if I'm a chemist or a material scientist, maybe I mainly focus on, tuning the material in order to get the interesting bending behaviors I want. I could change the stiffness of material based on which region the material is distributed. I could change the cross-linking, density. So actually, I'm gonna have a material scientist who come to talk about it later on. But if you are a, say, mechanical engineer or architect or designer who is more familiar with the language of geometry and structure, you could basically only tune things in on the geometrical level, but still get very interesting physical output and the programmability, so-called. In this example, for example, we're just using off-the-shelf, very cheap and easily accessible silicone. There's no material science, no chemistry. But then by just simply tuning the folding pattern, you can get all this interesting behavior. That's another way to think about programmability without being a chemist. And it's actually very essential to a lot of the morphing method we are introducing in the class. This is just to say what I just said again, more visually. So the pattern showing here is the folding pattern of the paper that's embedded in the bladder. And this is just an example of how things being used. Again, it's just a much longer strap that coils up. We also, on the piece of paper embedded in, we mounted some LED. So now you can, by pulling a strap, to turn it into a light bulb shape. And this is another example. So for this one, as you inflate, everybody knows how to inflate a balloon. So the difference of those balloons are the surface textures. You can see they have controllable surface textures gradually rising up as you increase the air pressure inside the bladder. And the way we did it is to basically laminate a piece of fabric on top of the silicone or latex, whatever stretchable piece of material. And by cutting different patterns of holes on the fabric, you could get different textures rising up from the surface. So again, this is what I said, a piece of silicone. But what we did is we then laminate a piece of fabric. It's also a stretchy fabric. It's called spandex. That's how a lot of the sports pants are made of, Lululemon, Nike, whatever. And then we just cut a bunch of holes with a laser cutter. Then you laminate together, but the fabric is less stretchable than the silicone. So as you are pumping in more and more pressure, you start to see the silicone are getting out of the fabric. So in this case, the material, right, is just silicone and fabric. The geometry is what I call folding pattern on the paper. Sorry, cutting pattern on the fabric substrate. Sorry for the typos. And the input is air pressure, and output now, instead of a bending, we're talking about pre-programmable bending curve. Programmable surface textures. And again, that's just to show how the cutting patterns on a piece of fabric can affect the surface textures you get. And why this is interesting, again, open your imaginations. You could imagine you're designing maybe a robot at home as a toy for kids, but have very dynamic, tunable surface textures for conveying different emotions of the robot. And another example, this is the aim is to do volumetric change. Maybe you guys noticed. So if you're talking about a soft piece of silicone, it's still very hard to control the global shape. For example, if I want a very rigorous cube, how you do it? This is one way to do it. You basically code a origami structure that has a very rigorously defined global shape with the silicone. So now the origami becomes airtight, and also the global shape is dictated by the origami structure. However, it's inflatable. And in this case, we are using, again, materials are the same. All the things we're trying to tune is on the structure level, right? we're doing this tri-layer thing. Basically, we're coating silicone on both top and bottom of the piece of paper, and we are also trying to control the origami folding to get the right kind of volumetric change we want. Yeah, please feel free to interrupt me if you have questions. So I want to talk a little bit about adapting human-centered design framework to fluidic morphing method. So up until this point, all the techniques are not only interesting to designers or HCII folks, but also interesting to McKee. So if you think about soft robotics, we have to do that level of structure manipulation, material tuning as well. However, they're not necessarily interested in kind of human-centered design framework where we're talking about human in the loop. So the idea is once we put it into a loop with human involved, we can think about more broader context where those methods can be used, especially beyond robots. And we have to then think about, right, what's unique about fluidic morphing method? Why Lining and Luca is spending 2.5 weeks to talk about it. So pneumatic actuation is one of the most classic type of morphing method, or soft method, if you will, because of many interesting properties of it, and it's unique. It's something that's trickier to do with, motors, let's say, all those rigid, hardcore, super powerful robots. So when we make things soft, it's soft. So it's compliant, and you feel safe. It's comfortable on your body, and also because you can leave the pumps that's as the source of the air, right, a little bit far away from your artifacts that human is directly interacting with. In a way, you could claim this is silent. You don't have electronics embedded in the interface you are directly interacting with. That's what I said. It could be electronic free. So when we work on the pneumatic stuff, there was a doctor who is the mom of a friend in the media lab back then. So she visited and got very impressed because she does MRI scanning for kids all the time. And she said it was very hard to hold the kids still in the MRI scanning machine, for pets as well, indeed. However, MRI, is magnetic reactions. You also can't get any electronics which will generate electricity and mess around with the magnetic field. So she got very hopeful to use those kind of pneumatic actuations to hold the baby in place because, again, it's safe, it's very comfortable, it's compliant, and your electronics can be just tubed away from the machine. So you guys can think broadly how some of the properties we're writing down here can be relevant to the scenarios you're interested in. And if you guys remember this Disney movie, maybe you remember also the day the Baymax was shipped, right? He was in a tiny box, and then it basically blew up and grew really tall. So the inherent compact packing aspect is real. That's why you can pack hundreds of balloons in a little bag for your festival celebration. It's also very rich in the shape manipulation, rich in a way that's unique. So if you think about motors, maybe you took some kinematic or robotic control class. So yeah, there are many degree freedoms you can control out of a motor-driven robotic arm, and it's very rigorously defined, mathematically speaking. But here, things are non-linear. It's kind of a little tricky and a lot of guessing and intuition along the way. How by just changing the origami pattern, folding pattern, you suddenly get this really organic looking coils. It's tricky to indeed model, and but however, on the other hand, it's rich. By a very simple geometrical parameter, you can get this very expressive shape transformation. And we want to acknowledge, the disadvantage, but also try to think louder. What are the possible advantages? And again, this is the one I was very excited to show when I saw one of your guys' videos from last lab. So this was a pneumatic-driven, like a phone, but it was very similar to the vision video you guys created. So yeah, basically, when you give the phone call, you stay curled, and then you can wrap around your arm. When you have to run out, when you need to do some more intricate operation, it becomes pretty flat and rigid. And as you can see, it's just basically a piece of paper with some hidden air bladders at the back. And all the metallic looking things are some capacitive touch sensors we put on top. Actually, this is literally the technique Luca gonna show you guys in the next lab. It's gonna be a little bit more primitive version of this, I believe, but you will learn how to do this. And if you want to carry it further, you can for your final projects. And I already, oh. This is just to show, this is a work from a really amazing group from Harvard Waste Institute. They do a lot of soft robotics and very tiny flying bees. This is one of their recent efforts trying to deploy soft grippers to carry very delicate or catch very delicate objects underwater, such as retrieval corals for biological purpose, biological sampling purpose. So again, this goes back to the selling point of pneumatic stuff is gentle and they could handle delicate objects. We also have friends who run startups, basically have pneumatic grippers to pick up food, eggs, or things that are very complex in shapes, or pokey things like those, desert plants. And this is a conformable haptic feedback scenario. Again, was developed by a friend back then. The idea was wrapping this with a bigger air bladder to give you bigger warnings. But then you can also have arrays of very smaller air bubbles to give you gentle haptic reminders. For the people who are biking, but who needs to watch the phone all the time to know the direction, now you can just through haptic to feel the direction, while your eyes can focus on the road and the traffic. And I talked a lot about texture. I also hinted a little bit. This is very interesting for the field of human-robotic interaction as well. This work was from Cornell and the Human Robotic Interaction Lab. So they basically try to embed some hard components within the silicone. So when you pump airs in, you get this interesting textures that have different morphological features. And those features could represent different emotional states of the robot, visually, but also haptically. And these are very essential topics when we talk about home robots, companion robots for kids, for the elderly. All right, I think that's my relatively brief review. And we, in the lab, we're big lovers of fluidic morphing matter. So I only can cover this little, but if you have more questions related to this, or if you want to read more papers, it's very rich, and there are many kind of fabrication design aspects you can dive very deep into. So for example, even just winding a non-stretchable thread around a piece of silicone, depending on how you wind it, you could also get different interesting morphing behavior. I'm not sure if Luca is going to show some examples like that in his lecture later on. So about the course structure for this section, I've already mentioned and warned you guys, there are going to be a lot coming up. So we have pretty much kind of 3 labs focusing on the topic of fluidic morphing matter. So on this Thursday, it's a relatively virtual lab. And so we are, it's another TH student who we're going to come and share a tool he developed to handle basically mesh-based structure that's triggered by pneumatics. And then for the coming Thursday and the coming, we have 2 labs, one on making pneumatic pouches and the other on controlling pneumatic pouches. If I have the time, I want to also squeeze in another way to think about pneumatic actuation, which is stiffness changing behavior. So basically, when you inflate, pump in air with positive pressure, you basically make things transform. But if you vacuum the air out, you could explore the stiffness changing property. So I'm not sure if you guys ever bought some of those vacuum bags. So when you have too many things you want to pack into a small space, you vacuum the air out, and then the whole thing shrinks in size, right? Also, I'm not sure if you noticed, it becomes super stiff. It's also like a coffee bag. Sorry, grounded coffee. Before you open it, it's also super tough. Once the air goes in, it becomes super soft. This has been deeply explored by people in the field as well as a way to change both shape and also stiffness. So if we have time, in lab 3, we can also squeeze in some of the stiffness changing stuff. We also have actually super exciting. Luca is already an expert. We have another expert that's a guest lecturer. So she's going to also zoom in, I believe, next Tuesday to talk about her recent groundbreaking work that got very viral online, basically using super thin pneumatic McKeven actuators to design yarns and threads, if you will, that can actuate. So you can weave or knit it into a piece of fabric for a lot of on-body fashion and interaction contexts. So yeah, she actually will zoom in from Europe. So a lot more to come, and there's also a lecture on computational design of morphing matter. It's not a programming class, but I also want to just kind of tell you guys by giving a lecture that a lot of the designs are based on intuition. A lot of hands-on making, make friends with your material in the lab. But you could also go pretty deep thinking about the computational and modeling aspects of those materials. So you will get a little flavor of that too. All right, any questions before I call a break? And then Luca will give a lecture as well on this topic.